In this video, we're going to talk about the rotational analog of mass. You might remember that last time we were talking about rotational analogs, and we were saying that the rotational analog of position is angle. The rotational analog of velocity is angular velocity, how many radians per second an object is rotating. The rotational analog of acceleration, A, is angular acceleration, radians per second squared, which we use the Greek letter alpha. And we had all the kinematic formulas for those. So you might be wondering, why would there be a rotational analog for mass? Isn't mass just a measure of how much stuff is in an object? And mass is important not just because it's how much stuff is in the object, but also because it's a measure of how hard it is to accelerate that object. So we have Newton's second law, which says that the acceleration of an object will be proportional to the net force on that object and inversely proportional to how much stuff is in the object. We also use mass in expressions like our expression for the kinetic energy, which is 1/2 mv squared. And we might get some insight into how this mass functions in this kind of expression by looking at kinetic energy as the way to understand the rotational analog of mass. So let's look at some objects. If I have a sphere like this, and I want to know how much energy it has by rotating, well, our standard formula would say that this doesn't have any kinetic energy because it doesn't have any v. It's not going anywhere. But I know that the top of the ball is moving, and the bottom of the ball is moving, and this side is moving this direction, this side is moving this direction. So when it rotates, there's definitely kinetic energy there. If I have a disk, it might be able to spin this way, can also spin that way. Those have different amounts of kinetic energy. A really extreme object might be something like this hammer, which I'll have a pretty difficult time accelerating this way, but it's very easy to accelerate the object if we rotate around this end, where most of the mass is concentrated. So let's see how we can understand the rotational version of mass by looking into kinetic energy. So let's begin by considering a wheel like this. If this wheel is rotating, I could say that its kinetic energy is just the sum of all the kinetic energies of the little parts that make up the wheel. So I have parts, different locations like this, and if the wheel's rotating this direction, I know that this little bit of mass will be moving that way, this little bit of mass will be moving that way, this one this way, this one this way, and we also know that mass closer to the center will have a smaller velocity, while mass further from the center will have a bigger velocity. So it's a simple matter, right, of just adding up all the kinetic energies of all these little bits. So let's see how that would work out. Well, the total kinetic energy will just be the sum of all the little bits of kinetic energy. So that'll be the sum. Let's suppose I have n total little bits, and I'm going to label them with an I. So from I equals 1 to big N, I'm going to have 1/2 m sub I v sub I squared. So that's each bit of mass and each velocity of that bit of mass. Anytime we can make something constant, like this 1/2, we could pull it through this sum and just multiply the sum by the 1/2 at the end. So that's a nice starting point. I can pull that 1/2 out. And now I know it's the sum from I equals 1 to n of m sub I v sub I squared. So unfortunately, these little bits of mass have different v's, like we said. But is there some kind of velocity that's the same for all the parts of the disk? We've just been talking about it. I know along this line, the further I go, the faster the velocity will be. But all of these will have the same omega value. So if this was mass 1 and it had radius 1 from the center, and this was mass 2 and it had radius 2 from the center, well, I could just consider these radii separately and think about the fact that omega is the same for all of these. So we know that the velocity of each little bit, velocity 2 here, would be radius 2 times omega. And here this velocity, velocity 1, would be radius 1 times omega. So let's rewrite v sub I here. I know this will be 1/2 the sum from I equals 1 to n of m sub I, and then v is r sub I omega squared. But I see that this omega squared is constant as well. So remember that kinetic energy, the linear kinetic energy, is 1/2 mass times velocity squared, and we already know that omega squared is the rotational version of v. So let's keep omega squared out there. I'm going to keep my 1/2 in front, and then I have my sum from I equals 1 to big N of m sub I r sub I squared. There's the sum that has i's in it, and then omega squared sits out here, outside the sum. So what can we do with this m sub I? I don't know how to sum up these little bits, so let's consider how to break up the circle in a way that makes a little bit more sense of that. We can add some coordinates to our wheel here, and let's say that each little bit of mass might be a little sector like this. How big is this shape? Well, we'll figure that out. I could label that the distance from the center to the infinitesimal mass is going to be called r. So this little size here is dr. What we're trying to do here is come up with an area that can integrate, meaning I can add up all the little bits of mass to end up with the whole wheel, but I'd like to have it in terms of some coordinates like r and theta. So this little angle here, if it's a tiny angle, we could call it d theta. D theta just means a change in theta, d for difference. So how big is this side of this rectangle? I already know that the radial side is dr. Well, the distance, if this is infinitesimal, it means it's going to be approaching 0 as a limit. But I need a side here that also approaches 0. Well, this side is r times d theta. You might wonder, why is it r and not r plus dr times d theta? Well, when dr is vanishingly small, I can consider r to be the distance to this tiny thing that actually has no area, but we'll be able to write the mass of this thing because I know the mass is just going to be the density of the wheel times the little bit of area, dA, the area. So what is the density of this wheel anyway? Well, I know the density is the mass divided by the volume, and since this is a two-dimensional wheel, the volume is really just the area. So the density is the total mass of the wheel, we'll call it big M, divided by the area of the wheel. So what is that? Let's say that the whole radius of this wheel will be called big R. So the area will just be pi times big R squared, right? So that's the density. And now the next thing we want to do is write what is the amount of mass in this guy, the amount of mass which we'll call dm. And I can replace this little m sub I in here with a dm, and it'll have r's in it, so I can combine those r's with this r, and it'll give us a way to add this up. So I see that my area looks like a rectangle, even though I know it looks like a little sector with two curved edges and two straight edges here. In the limit that these are really tiny, all four we can consider to be straight. So this dm is the density rho times the d area. What is that d area? Well, it's r d theta times dr. So we'll call it r dr d theta. And this thing here is the area of that little rectangle. This is the density, so if I take the mass per area times the area, that'll give me the little bit of mass. So we can say that this sum, in the limit that this number of particles goes to infinity, but their size goes to 0, becomes one of these guys, becomes an integral that includes all of the mass of r squared dm, where dm is located at that r. So rewriting this dm in terms of r's that can be integrated here, we have 1/2 the integral that includes all the mass, and we'll figure out how to write that in a minute, of r squared, and then dm, we've got it right here. It's the density times r dr d theta. So I'm getting pretty close to my camera here, so let's clear out a little space and we'll come back to the top here. Continuing from this expression at the bottom, let's figure out what this this total sum is going to be. I see that it's going to be, well, first of all, this 1/2 is not part of our calculation here for the analog of mass. That was just sitting in front of our expression for the total kinetic energy. So to include all of this wheel, I need to integrate my d theta. How far do I need to integrate it? Well, from 0 to 2 pi. That'll get me all the angle. And then my integral of r needs to go from a radius of 0 to a radius of big R. So to include all this area, we need to include all of the radius from 0 to big R and all of the theta from 0 to 2 pi. Notice that theta doesn't depend on r, and r doesn't depend on theta, so I have two integrals that don't depend on each other. I can do them in either order. So we're going to integrate d theta from 0 to 2 pi. You can probably do that in your head. Integral of d theta is just theta. And we're going to integrate all that stuff with r's in it. I see this constant here can just come out front, the density. So we have, what's left? We already took care of our rho just now and our d theta. So we have r, 1, 2, 3 r's, and a dr. So this will give us r cubed dr, and our bounds, remember, are from 0 to big R. Let's evaluate. We have rho times the integral of d theta is just theta. Plugging in my theta at 2 pi minus my theta at 0 gives me a 2 pi. And integrating r cubed gives me an r to the 4th over 4. Plugging in my bounds, I have then big R to the 4th over 4. And that's the expression. We just need to plug back in our value for the density here. So our total integral is going to be m over pi big R squared times 2 pi times r to the 4th over 4. I see some things can simplify here. Our pi's are going to cancel. 2 factors of r are going to cancel. And this 2 over 4 is going to become a 1/2. So we have 1/2 big M big R squared. So this thing is the rotational version of mass for a disk like this one, rotating around its center this way. So let's look at that expression for kinetic energy, total expression we have. We had that the kinetic energy for this disk, rotating about its center, is going to be 1/2 times the value of that integral that we did, which remember was the integral of r squared dm for the whole object, times omega squared. Different objects have different moments of inertia, and it also depends what the object is rotating around. So I, for a rod of length L, it's rotating around its end, it's going to be 1/3 the mass of the rod times the length squared, and that's around its end. If the rod is rotating around its center, it's a much smaller value, 1/12 ml squared. You can try this out if you have something like a rod. if I rotate this rod around its end, it's a lot more difficult than rotating it around its center. For a sphere, rotating around its center, the moment of inertia is 2/5 mr squared. So notice the units of this thing are always going to be kilograms times meters squared. This quantity I also comes up anywhere that we would use mass, in kinematics or in dynamics. So whereas we had acceleration is equal to the net force divided by the mass, angular acceleration is going to be the net rotational version of force, which we call torque, divided by the moment of inertia. Or in the form you often see these, Newton's second law, F net equals ma, and torque equals I alpha. Similarly, in this video, we showed that the kinetic energy is 1/2 I omega squared, and the same way that linear momentum is mv, angular momentum, which gets a capital L, no one knows why, is I times omega. So that's an introduction to the concept of moment of inertia, which is the rotational version of mass.